Okay, so first of all, thank you very much for being here and being interested in lasers. I find that they're amazing tools, that there's lots of things about them which are completely unknown to the wide public, although they're really ubiquitous in popular science, in science fiction books and movies. And so I really wanted to share some things that I find really, really interesting about them. So my talk is called Know Your Tools. So I'm firing my laser. Unfortunately, I forgot my laser pointer at home, so that's the first time I'll be pointing with my finger. I hope it's okay. Right, so let's dive into the subject. I'm not going to give you a lecture. Cheers. I'm not going to give you a lecture about laser science. What I want to give you is a very partial overview and very biased overview of what I find is underrepresented in popular science about lasers. So there are some laser applications in our everyday lives. So some of them you probably know very well. So the laser pointers and the laser machining for your cutting, engraving, welding, drilling, and the bubblegrams, all these interesting things you can do with lasers. The laser meters, the gyroscopes, accelerometers, computer mice, you name it. So many applications with continuous lasers. And then there's some which are a bit less well-known, which are pulse lasers, which means that the energy comes out in a very short amount of time. So you might have the same average power, but actually all the energy comes out in a very, very short amount of time. So that's used for laser drilling to have very, very low heat deposition into the material. Or for surgery, so that can be eye surgery, that's probably the most well-known, but there's other applications. So you've seen all the different applications, all this world of applications that you can reach with lasers. And somehow all these lasers are lasers. So what makes them special? What's the common point between them? So if you just need to remember one thing about this talk, what's special about lasers is 1, brightness, high brightness, and 2, high coherence. And so I will go over these two subjects and we'll make things clear, don't worry. So first, we'll cover the easiest topic, which is brightness, because that's presumably the easiest to understand. So what do I mean by brightness and how do you quantify it? So first of all, we start with a light bulb, a 100-watt light bulb, and you shine it onto a mouse. So you do that with a light bulb, not a laser. 100-watt laser light on the mouse is not okay. Not okay. You do that with a light bulb, and then you do that with an elephant. So you start with 100-watt and 100-watt on both sides, but the mouse is way closer. So if you look at the energy per second per square centimeter of the mouse, there's more than on the elephant, because the elephant is further away. So that's quite clear. So the brightness on the mouse is higher, because the amount of energy per square centimeter is higher on the mouse than on the elephant. So basically, to make it a bit clearer, it's brightness is density of energy in time and in space. So this is the brightest direct sunlight on Earth. You get 300 watts per square meter. You don't get more than that. So that's like at the equator on a completely clear day. And then if you look at your green laser pointer that you have in your pocket, then it's the same brightness. Of course, it's not the same amount of energy. There's a lot more energy coming from the sun than from your laser pointer. But the brightness, meaning the amount of energy per second per square centimeter, is the same on your laser pointer as it is from the sun. So that's an interesting fact to know. So now, which applications make use of this laser brightness? So everything that cuts, slices, drills is going to make use of this brightness. You can concentrate a lot of oomph, a lot of energy in a very small space, which means that you can make very precise cuts. So there's laser pointers, of course. There's laser guides for astronomy and LiDAR, which are light radar. So I'm going to talk a little bit more in detail about one of these applications, which are laser guides for astronomy, because I find that they're way cool. So before I do that, I want to tell you about adaptive optics. So it's a little bit of an incursion into a different topic. So adaptive optics is something that's a bit magic, but that works, and that allows you to see objects in the sky that look a bit strange, and you want to know about their structure, and you want to have a very high resolution. So if you take your home telescope and you see this weird object in the sky, and you're thinking, okay, I want to go and get a very big telescope so I can resolve this object. I really want to know what it is. And so in between you and the sky, there's of course the atmosphere, luckily, because then you can breathe. But it has a drawback, which means that, so this drawback is that the atmosphere moves all the time. There's wind, there's changes of refractive index, and so it distorts your image. And so if you take your very large telescope, your favorite one in the world, and you don't do what's called adaptive optics, then you see a blurb. And so basically, having a telescope that's larger than 30 centimeters is useless because of the atmosphere. And so this is what you get. If you had like a binary star, you would see this. And this is actually like real picture. So now what's adaptive optics? So you take light coming from a point source, so from a star that's really far away, and you know what to expect. You know what sort of image to expect. You expect a point. And then you can, there are ways to see the distortion of the image coming from the star, from the atmosphere. You can find that. There's something that you can measure, and you can infer what is the deformation that was applied on your image. And so the method goes as follows. You measure in real time this atmospheric turbulence, and then you apply the inverse to a deformable mirror inside of your telescope. And all big telescopes in the world are equipped with such deformable mirrors. And so you apply the inverse, and then you can enjoy the view. And to give you an idea of what it looks like, so this is all real, you have on the left without adaptive optics, and on the right with. So that's pretty striking. It's how well it works. So now, where are the lasers in this story? The lasers come in when you want to observe an object that's really distant, really far away, and unfortunately, there's no bright star around. So what do? You have to create your own star. How do you do that? Well, it turns out that there are some sodium atoms about 90 kilometers above the ground, which are in the form of sodium oxide, and they come from the ablation of meteors in the atmosphere. And so you can see this layer of sodium oxide, which you can excite with a laser. So you shine laser in there, and it will go all the way through this layer, be absorbed there, and then you retrieve the light that comes back. And from the light that comes back, you can make sure that it's bright enough. From the light that comes back, you can infer the deformation that came from the atmospheric turbulence. So this is where lasers come in, and this is what's used at the VLT. For example, you can see this beautiful yellow beam, so it actually is yellow, because sodium has a yellow resonance. We probably see that from sodium lights in the city. So which applications make use of laser brightness? So I mentioned laser pointers, laser guides, and then you can go up in oomph. So the next step in oomph are the cute CO2 laser cutters, about 10 to the 8 watts per square meter, and then the high-end CO2 laser cutters, which are about 10 to the 10 watts per square meter. Of course, you never have this amount of wattage on the full meter. Most of the time, it's focused on something like a few tenths of microns. So it's obviously not, you're not getting 10 to the 10 watts. That's not what you're getting. So then, if you want to go higher in brightness, you want to increase the amount of energy per second per square meter. When you can't decrease the amount of square meter, then you need to decrease the amount of seconds. So there are tricks to make the lasers brighter by going from a continuous wave, which means you have a certain average power, and the energy that comes out is always the same. Okay, you have this continuous flow of photons, this continuous wave. But then what you can do with the same average power is to wait for a long time, nothing happens, and then suddenly, I don't know, a few femtoseconds or more, but yeah, the shortest are a few femtoseconds, you get all this energy all at once. And so that's a pulse laser. And pulse lasers are very, very powerful tools to allow you to get extremely, extremely high brightness. So then, so I'm a research engineer. I work in a laser lab, and we get 10 to the 22 watts per square meter with our laser, which is sort of cute. It fits in a room that's about this size. And then you have the brightest lasers around. So the brightest lasers around are not to be fooled with. They're 10 to the 23 watts per square meter, and they look like that. So that's a full-blown installation of the size of a small accelerator. And so this one is the ELFX at Osaka University. So what the hell do you use that for? You use that to emulate the conditions that you would get in outer space, so very extreme plasma conditions. So it's basically a way to get laboratory astrophysics. This is a person. So yeah, you can imagine the size. So it's not like a small laboratory. It's really a full-blown national project. So this is the headlines from the Mail Online. The Death Star weapon is here. Japan fires world's most powerful laser. So there's interesting things like it produces an energy equal to 1,000 times the planet's power consumption. So this lets you reflect on this. Is quite entertaining. So that's what the media make of that. So there was a little side note. Talking about the Death Star, so if you're asking me how much the Death Star would be, it would be something like probably 10 to the 45 watts per square meter. It's a rough estimate. And then for the crazy scientists, they're the future multi-exawatt lasers, which are in people's wildest dreams, and some people dream really far. And so that's about 10 to the 29 watts per square meter. And so those are so crazy that if you focus them in vacuum, then they would allegedly be able to extract pairs of particles and antiparticles out of vacuum. This has not been proven. The experiment will have the last word. See you in 30 years. Then, okay, that's it for brightness. So you could see how bright could be. And now we're going to talk about a topic which is not so pew pew, which is a bit more about something that's a very subtle quality of lasers, which is coherence. So I really like coherence. So first of all, let's talk about something that's incoherent. Incoherent is everywhere. Everywhere is chaos, as you all know. So there's from a light bulb, there's lots of photons coming with many colors. They come at random times. It's extremely chaotic. And then if you take a laser, the simplest image that you can have of a laser is basically this stream of photons. And if you look at it as a wave, then it's this wave that just carries on forever, and it's a sine wave from the beginning of the universe till the end of the universe. It's not that simple, but that would be a perfectly coherent wave. So this is a perfectly coherent wave. On the left, you have the beginning of the universe, then the end of the universe, and everything in between is a sine wave with always the same frequency. This obviously does not exist. There's everything in between. And so if you have a less coherent wave, so say your wave starts and it has phase jumps and you have multiple frequencies that come at random times, so this is what it would look like. So this would be the electric field of the light that comes out of some fairly incoherent laser. And so that's more incoherence, and then that's completely random. So those are like all the shades of yellow that you can have between perfectly coherent and perfectly incoherent. Now, you might know this from laser pointers. So this is a direct consequence of having coherent light. So basically, if you shine torchlight on the wall, you're never seeing that sort of thing. It's just with a laser pointer that you see that. This is laser speckle that you only ever see with coherent light. That was a side note. So coherence is something that you can harness to measure time. So I'm going to give you some slightly in-depth example of how that's done. So say you have your wave, it's perfect. And then at some point you stop monitoring, take your stopwatch, you wait for a while, and then you stop your stopwatch and you look at your wave again, and you can know exactly at which point of the cycle you end up. This is with a perfectly coherent wave. And so if you have such a thing, then if you count the number of cycles in 1 second, then you have a very accurate measure of frequency. And then conversely, if you have the frequency, then you can define the number of cycles in 1 second. And so we'll see how that property can be used to define time and to define the time that we are using to define the second. And so this application is called atomic clocks, and the newest advancement in atomic clocks are optical clocks. So I'm going to give you an overview, so bear with me. It's a very in-depth topic, and all the devil is in the detail, and there's lots of details. So this is an atomic clock at Sirte in Paris. So this is about 1.50 meters or something like this. I don't remember exactly the scale. So it's fairly large. And so this is the clock that gives France its time. It gives it its second. This is the second that we have, and it's shared with other countries. So I'm going to talk to you about them because I find that they're really beautiful. They're a bundle of so many beautiful techniques, and then they're amazing because their drift is less than a second in 100 million years. So that's extreme precision. So first of all, to make a clock, you need a resonator. So in the old days, Huygens came up with a pendulum clock. So it went tick, tack, and that's a very well-defined frequency. And then to go further in accuracy, people decided to take a quartz resonator, and to make it even more accurate. Maybe if you do RF, you know about these techniques. You just make the temperature always the same. You put it in an oven, and it makes the frequency extremely stable. And then you can take an atom, and an atom is also some sort of resonator. So if you take an antenna and you throw some resonant wave, a wave that's resonant with the antenna, then you get an output. And then with the atom, it's more or less the same. If you hit the resonance, then the wave that you're sending in will be absorbed. And that's a signal that you can monitor. This is something that you can measure very accurately. So to make a clock, say you take a cesium atom, so that's the atom that was chosen for a variety of reasons, and then you hit the cesium atom's resonance. And you say, okay, this frequency is going to be 9.192 blah, blah, blah gigahertz. So this is in the microwave regime. So you say, this frequency is going to be that. That's the decision. And then you count the number of cycles over time with very precise counters, which you have with radio frequency technologies. You count the number of cycles, and there you go. You have time. You have defined time from your resonator, which is your atomic resonator, which allegedly or supposedly doesn't change. And so far, it has been proven that it doesn't change. So those are the first types of atomic clocks. They're cesium beam tubes. They work with hot atoms. And they allow you to have an accuracy of a second in 1.4 million years. So, of course, people want to get that better. So what do you do to get that, to do that? Of course. What do you do to make that better? So, as I said, this works with hot atoms. And hot atoms have, as a result, different velocities. And this variation of velocities will change slightly the frequency of the resonance. And so a solution is to cool these atoms. And it turns out you can do that with lasers. You can cool atoms with lasers. Maybe some of you have seen that in laboratories or even work in them. So to give you a rough explanation of how it works, you have your atom sitting in the laser beam, and then photons are bombarding the atom, and so it gets pushed. A bit like the comet tail. So maybe you have seen pictures like that with the tail going away from the sun. It's because all the particles coming from the comets are pushed away from the sun by the solar wind. So it's exactly the same principle. This is called radiation pressure. And so if you put beams in all directions, so I need to hold the microphone, but yeah, you see from the drawing, if you take beams from all directions, then you can trap the atoms. So this is a magneto-optical trap. So here I have obfuscated some details, like all people who give lectures. I lie a lot, hopefully not too much. And so it's a bit more complicated than that, but more or less you put magnetic fields, and this allows you to trap atoms in the crossing point of your laser beams. So this is at the center of this chamber. You can see this glowing ball. That's the atoms, and you can see the blue beams. So that's quite pretty. Magneto-optical trap with blue beams. So then, when you've applied these techniques and others, you get to something that's called an atomic clock, and this one is actually an atomic fountain, and they allow you to reach an accuracy of 1 second in 100 million years. So this is extremely impressive, but people want to get better. So when that's too much, then what do you do? What do you do? Do you try to decrease the uncertainty? Is that what you're trying to do? Okay, well, you've gone so far, and there's no way you can decrease the uncertainty. That's the absolute limit of electronics, the absolute limit of everything. But what you can do is increase the frequency. So this is, as I said, for the cesium atom, this is 9 gigahertz, about 9 gigahertz. So 9 gigahertz is radio frequency or microwave, and the technology for microwave is extremely well advanced. So that was quite practical because you had very good tools to start with. Nevertheless, if you want to increase the frequency and go from microwaves in the gigahertz regime to optical waves, say 300 terahertz, then you encounter a new problem, because it's very, very difficult to have an accurate measurement of optical waves. You don't have a counter, you don't have a photodiode that you put in your beam and is going to monitor your optical wave. That's just never going to happen. So what do you do? Well, there is a solution, and it's called optical frequency combs. Yeah, that's what they look like. This is amplitude on the y-axis, and the axis is frequency. And actually, you don't span the full range from 0 to infinity. It's actually a bandwidth that you have. So this is a Mickey Mouse version of a frequency comb. You have many more teeth for a given bandwidth, but otherwise it would be invisible. So this is a schematic. So in principle, if you knew one of the teeth extremely precisely, and you know the interval, and the interval between the teeth is actually not so difficult to know. But if you know very precisely one tooth and the interval, then you know all your comb, and then you can compare all frequencies with one another. So that would be great. But it turns out that knowing exactly the frequency of one tooth, knowing it exactly, is extremely difficult. However, if you look at the detailed structure of the comb, so what is this? Okay, so in red, that's the real comb. In blue, that's the comb that's extended from 0 to plus infinity. So that's what it would look like. Everything in blue does not exist, but it's information that can be retrieved. So if you look on this structure at the 0 frequency, it turns out that you have this very well-known interval, and you have an offset. And so this offset and the interval are the only things that you need to know to define your comb. And it turns out that this is a radio frequency, and we have very good references for radio frequencies. They're atomic fountains. So now the trick is that you apply some optical magic to be able to retrieve this part of the information that's within the comb, but that's not actually there. You can just retrieve it from some processes. Then you can lock the comb on an atomic fountain. And then you can reach crazy levels of accuracy, which are 3 × 10⁻18. And so that's the results from 2016 from the PTB in Braunschweig. And so this is the absolute record of accuracy in optical clocks. So now to wrap up, I hope I have convinced you that lasers is not only about cutting, drilling, and slicing, and that it's applied to very, very fine applications such as astronomy and frequency standards. There's one application that I've not talked about, and that's just because I don't have the time, which is gravitational wave detection, which was also a discovery that was due to lasers. There's particle acceleration, quantum information processing, hair removal. That's a very important one for the laser industry because it produces a very high turnover. And then there's obviously making holograms on chocolate, but that's for next Easter. Thank you. I'm taking questions. No questions? Okay, great. So if you have any questions, I'll be hanging around. I'm quite approachable. Thanks a lot.